Hope you are well, used your break wisely. And as I mentioned before, what I'm going to do today is to focus on a special kind of function series, which is called power series. We don't actually need to remind anything from previous lectures, but we will talk about uniform convergence, etc., but probably not today. So, what is a power series? Um, a function series of the form sum. We start with 0, to sum with 1 or 2, whatever, will probably be the same. An x minus a to the power of n, where an is not dependent on x, just on n maybe, is called a power series because it contains powers. Power series around a. We are already know. We already know some. We have an example for a power series. Is the geometric series. The geometric series is for example, let's write down that way. For example, the geometric series is a power series. One can write down x to the power of n as 1 multiplied by um, x minus 0 to the power of n. So it's a power series around 0, where all of the coefficients are just 1. I want to write down another examples just for us to understand precisely what do I mean when you talk about the power series. So you write it down, definitions. It's the same, right? But there's another something to sharpen here. Another examples. Now let's write down. For example, first example, it would be 1. Second example, something ugly, so you can write it down. N goes from 2 to infinity, minus 1 to the power of n multiplied by ln n, x minus 8 to the power of n. Here, the coefficients an are minus 1 power of n, blah, blah, blah. And a is 8.
But oh, it's not dependent. Okay.
Yeah, not on x. It can be dependent on n, but not on x. One can argue that by definition, the sum should start at 0. And here the sum starts at 2. But this prepare you to the next example. Every sum that starts at 2 is actually a sum that starts at 0. How? The first two elements of 0 and 1 have a coefficient 0. Let's see, note. And write this sum can write this sum as starts with 2, and then n equals 3, then n equals 4, etc., etc. But one can write down also the powers of 0 and 1, just multiplied by the coefficient 0. So every power series can be started, if need be, from 0. But moreover, I want to show you example number 3, which is a series that we will encounter later. Not today, but we will. Minus 1 to the power of n, say above 2n plus 1 factorial, x to the power of 2n plus 1. Here, the difference between our series and the basic definition is the power. I mean, yes, you can write it down as x minus 0 to the power of 2n plus 1. We already did it with the geometric series. We know that when it's only x, means that the a is 0 in our definition. But how do we deal with the fact that the powers here are only the odd numbers? Now, on first sight, associate in English? In first sight.
Yeah.
On first sight. On first sight, there are only odd powers, which is not exactly how a power series should look, but just in the example number 2, but we know better. Every power, every even power do, oh, the power, the even powers appear in the series as well, just with this is right, it's coefficients 0. I mean, right here, one can write it down as the sum of minus 1 power 0 above 2 multiplied by 0 plus 1, which is 1 factorial, and x to the power of 1 plus minus 1 to the power of 1 above 3 with x to the power of 3. And we do have the place at the time, so let's write down another element responding to n equals 2, which is 5, and so on. Well, you can write it down as 0 multiplied by x to the power of 0 plus, and 0 multiplied by x to the power of 2 plus, and 0 multiplied by x to the power of 4 and plus, etc., etc.
But do we need to transform it, or can we just state that, like?
Oh, that's a good question. Do we actually need to write it down explicitly with the zeros or in any other way? Or is it enough to know that even though the powers are not exactly n, the series is actually is actually a power series, and we can work with whatever power series working with. Um, we have this lecture, next lecture, the lecture after it, and maybe even the 4 lectures from now. Let's see how we roll. Talk about power series and what do we want to do with them, and why are they good, why are they bad, etc., etc. And in some of the cases, it is sometimes important to notice that there are actually coefficients that are zero. In other words, the power of x minus a should be exactly n and not something else. And we'll probably see an example for such a thing later on this lecture as well. And getting to here, one can say, you know what? I can write down as the sum going from 0 to infinity of an minus x to the power of n, where a is just 0, and what is an? Maybe we use different letter, or use the n for the first way. AK is, okay, it depends. If k is an even number, then it is 0. And when k is an odd number, it is this thing. This thing. Uh,
To use something that has to go on this function.
what?
Economic function.
Instead of?
Oh, when it's like this, like doing two different values depending or even on.
I want to write it down not as
I mean, yeah, just as like
piecewise function, but with something
yeah, like
neat and
say,
clean.
yeah, like clean.
One can do something like that probably. Yeah. Yeah, sinus pi n above 2 or pi n plus 1 above 2 or something. Yeah, but there's no need of that. Here this is a leaks way space up things. Moreover, generally speaking, generally, if we have some Bn is a subsequence of n, then we can think of the series with Bn in the power as a power series where every missing power is there just with coefficient 0. For example, let's write down in a different color. We start to talk too much about it. Preferred color. Yeah. Okay, let's work with the two. Let's say we have simple series starting from 0 to infinity. The coefficient is just 2, and x is in the power of n squared. So you can write it down as 2 x to the power of 0 plus 2x to the power of 1 plus 2x to the power of 4 plus blah, 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 blah. 2 to the power x to the power of 9 and so on. And it is actually a power series because we can add up every missing power with 0 as its coefficient, right?
Here is a sequence that is not That's sometimes follow any particular characteristic, so we can.
Yes, an can be whatever you want as long as it is not dependent on x. Whatever expression of n you want, for whatever n, for odd n it's that, for even n is that, for this n is this, whatever. But the formation of x minus a to power of n should be is necessary. And now we already know that in order to understand things better, we need to see some counterexamples. What is not a power series? So this is going to be 4 before we move on. On the other hand, some examples for function series that are not power series. You name it, whatever many of the things we've seen last week probably will make do. Ln of 1 plus x squared above n squared plus x squared plus 6 or something like that. We've already done uh, previous lectures. It is not x to the power of something, right? So what can men do? 0 to infinity arctan of nx, and even more, one can think of something that looks like more of a power series, but it is not a power series. For example, if we take x and in its power, put something uglier than a subsequence of n, let's just say square root of n. This is not a power series, not like by how we define it. X to the power of sinus n, sinus square root of n, whatever.
Um, to be in the number.
Yes, but the basic definition talks about the natural numbers. 1, 0, 0, 1, etc., etc. We concluded that if it is not all the natural numbers, just a subsequence of them, only the squared numbers, only the odd numbers, etc., then it is also fine, because whenever power is missing, it is there, just with coefficient 0.
Yeah, a subset is fine, but like square root of n is not fine because it's not
Not a subset, a subsequence. A subsequence is a subset that actually behaves like a sequence. I mean, it is increasing.
Yeah, but for the square root of n where the square root of n isn't a natural number.
No, so it is not a
Okay.
power series.
Okay.
Those are examples for functions that are not powers by our definition. Okay, so what is so nice about power series that they are requiring their own discussion? Two things, probably three. They are not exactly polynomial because it is a series, not just a summation. It's infinite numbers of elements. But there is something nice about their pointwise convergence. That's what we will discuss today. And something nice about their uniform convergence next week, Bezrat Hashem. And we can use them to approximate many functions, irrational functions, which is always great. We'll talk about it next lecture or something. Okay. Let's write down the domain, convergence domain. Convergence domain of power series. It's the nice thing. We can define it not just for power series and even not just for series of functions, we can define it for sequence of functions as well. Domain of convergence domain for what values of x from the real numbers, the sequence, the function series, the power series converges. So let's write it down. Let sum f and x be a function series. Oh, with a, without a, no, what to. It's plural, it's not plural. What the hell? Function series, the convergence domain of series is the set, now A, and then is I. So right away, why? I in R of all x's in which the series converges. For example, the converges domain of the geometric series, we know from a previous CFE1, which was great fun, it is -1 to 1. Now, what is so special about power series when it comes to the pointwise convergence, about for which values of x the series is convergent, is that their convergence domain is of one specific form, not specific set, really sets that can be the convergence domain of some series, power series, but of actually one specific form. And this is my proposition. Let some an x minus 1 to the power of n be a power series, and let I be its convergence domain. Only 3 cases are possible. And in hindsight, we will see that it's actually only one case. They're all the same. First of all, can be the series converges for every x. The convergence domain is all R. On the other hand, it is possible as well. The series converges only in A. Know that when you put your A instead of X, you get series of zeros. It is always convergent. Convergent at A, whatever the AN is, whatever the power is, as long as it X minus A, of course. And the most interesting case is there is an R, let's go down, a symmetric interval around A. In other words, there is a number R such that I is one of the following options. The open interval around A minus R plus R, the closed interval, and it can be one open end and one closed end, and vice versa. For example, the convergence domain of the geometric series that is, as we already written, x minus 0 to the power of n. So 0 is the center of the domain. Is minus 1 to 1, but one can write it as minus 1, as 0 minus 1, 0 plus 1. So here, this r is 1. Take one left, one right from 0, you get your convergence domain. R is called, that's pepper, said before. R is called the convergence radius of the power series.
Right.
Yeah.
So for the first two cases, A is for the sequence A and having an infinite amount of zeros, right? Like was the real number.
No, not necessarily.
Then what allows it to converge if it's not that the sequence that's
For example, you can look at some, let's say, the series, we will encounter it later on, 1 above n factorial, x to the power of n. Whatever x you put in, the factorial is stronger. Takes it to 0, and it's convergence. On the other hand, one can look at n factorial, and that's it, multiplied by xn, and it only converges when x is actually 0. R square the convergence radius of the series. Okay.
Can I ask a question?
Yeah, of course.
Can you explain B? Like, I don't understand how is I equal to if I is the domain, then it can't just be one number.
Oh, why not? I mean, uh, talking about the notions, a domain can be, no, the domain of function and so on. Domain can be a set with only one element. And about the specific case here, we talk about the numbers, the values of x in which the series converges. For example, one can look, as we mentioned, one can look at the series of n factorial multiplied by x minus n, or x minus 8 to the power of n. Whatever x you take, as long as it is not a, the factorial is stronger than the exponential, and it takes it to infinity when the series is divergent. The only one and only point in which such a series is convergent is where yeah, I don't know. Went to sleep. I don't understand. I started to say, in this example, the only point, one and only point in which the series is convergent is x equals a, nothing more. So the domain, the set of all values of x in which the series is convergent is only a. And it can happen. What's the weird? I don't think you can see it. No, but I see it on my computer. A weird yellow something about around the. Okay, he's gone. Um, somehow he's gone. Any other questions? So before I prove this theorem, I have to show you the other way around. Yeah, the other side of the coin, which says in Hebrew. What, for example, can on the other hand, for example, sets like, I don't know, 2 points, and that's it. The interval from 0 to infinity. All are, but missing some 1 point. Number you don't like?
7.
Okay. The union of two intervals and whatever you can think of, are not the convergence domain of any power series. They're not all R, they're not only 1 point, and they are not a symmetric segment, theoretic interval around some A. And from another approach, if we look at some simple function series that is not a power series, let's say we look at the sum n goes from 0 to infinity of sinus x to the power of n. We know it's actually a geometric one, but it's not x, it's sinus x, is convergent if and only if sinus is equal or lesser than 1, but absolute value, which is true if and only if sinus is not 1 or minus 1. So x is not half of pi no plus pi k. For every x that is not pi above 2 plus pi k, the series of sinus x to the power of n is convergent. So here we get that the convergence domain of the series is all of R without the points of pi above 2 plus pi k. And again, when it comes to a power series, it cannot be its domain of convergence, whatever the series is, because we only have 3 options when it power series, an, xa, x minus a to the power of n. All of the real numbers, only 1 point, or a symmetric interval around a. Now, what I want to say, now we can think of I to be all the real numbers as the case in which the radius is infinity. You go infinity right, infinity left from A, and you actually cover all of R, and of the case in which I is only 1 point as the case of R equals 0. In A it is convergent, hooray. Take 0 left, 0 right, you're only left with A. So, as I mentioned, it is actually only one case. You got some R, then you know what the domain of convergence should be. If R is infinity, it's all of the real numbers. If R is 0, and it is only 1 point, and if R is a number like 1 in the geometric series, then it's a segment, a symmetric segment around A. Do we know right away if the segment contains one of the ends, yes or no? We'll discuss it later. How do we actually find this? How do you actually find this radius of convergence? And how do we use it to conclude what is the domain of convergence? And before we do that, I want to prove this proposition. Squeeze my finger in this shitty bottle. It used to be black, all of it. I used to be young.
Do you
Yeah.
restart the recording?
Yes.
Okay, I'm just checking.
Yeah, I don't know, the cloud with the little red eye inside works fine. Now, if I did do start recording on time, the fact that I have two computers uh, assure that the recording continues, even though one of them says bye bye. Like what happened linear. This one when the electricity went down, or whatever it was. Okay. So as I mentioned, I want to prove this theorem, this proposition.
Can I ask a question?
What? Yeah, I can. Yes, you can.
Um, the thing where you write about sine, shouldn't it be if the absolute value of sine x is strictly smaller than one?
Yes, yes. Of course, you're right. Of course, of course. Exactly. Any other questions? Notes? Corrections? Okay. So I want to prove the proposition, but in order to do it, I want to phrase it a bit differently, rephrase it. What do we actually say here? Yeah. Use a little drawing. Not something important, I deleted later without uh, putting it back here in the leaks, but you should see it. Let's say this is the real line. We have our center A here, and let's say we have some B in which we know the series is convergent. You put B instead of X, you get the convergent series. Now, what do we actually stated? That the convergence domain of a power series is actually an interval. Not every interval can be so, interval symmetric around A. What do I mean by interval? I mean, if we know that the series is convergent here at B, it should be convergent in every point between A and B. Moreover, we talk about a symmetric interval around A. So whatever this distance is, you take this distance here as well, and the series should be convergent in these points as well. In other words, that's what we are actually going to prove. If we take what are we actually saying? If the series an x minus a to power of n is convergent for some b, then it must be convergent for every c that is closer to a than b, meaning that the distance between C and A is smaller, strictly smaller, than the distance between B and A. If we know that series is convergent in B, and that C satisfies this inequality, then the series must be convergent at C as well. So we know that in that way we get a symmetric interval around A, all the interval, without any holes or whatever. So we know that the series is convergent at B. And that C minus A is smaller than B minus A, semicolon. We need to show that the series at C is convergent as well. This different approach to the same thing. That is what I am actually going. I do need to put wrote it down nicely. I need to do it. Okay, so how do we do it? Intuitively, the series with B is convergent, and the series with B is greater than the series with C. So comparison test. The problem is that we do not know anything about the absolute convergence of the series with B, and we talk with absolute values when it comes to the relation between B and C. And moreover, AN and C minus A can be negative numbers, so we cannot use the comparison test. So how do we uh, overcome this obstacle? As we already did in this course at least one time, we need to talked about the connection between the integral of absolute value of f and the absolute value of integral, and something like that. Lecture number 5, lecture number 10 about Dirichlet. Or was it lecture number 9? No, it was 10, I think. Now we do something differently. First of all, we show something even stronger. We show that the series is absolutely convergent. It is enough. It is enough. Let's go home. It is enough to show that the series of absolute values is convergent. And we use the following tick. First of all, we can write it down as the absolute value of AN multiplied by the absolute value of C minus A to the power of N. Absolute value is a multiplicative function, so it's powers and multiplication. We can put them in, put them out as required. Now the stick, I multiply and of course divide the series with b minus a to the power of n. That way, I can write it down in the following way. On one hand, it is an multiplied by b minus a to the power of n. And on the other hand, it is c minus a, and using some rule of powers, we can take the n outside. Taking for a walk. Well. What do we have here? If we look only on this expression,
Zero.
it is not, what means zero?
Isn't it zero? Because the smaller than b and
It goes to zero when n goes to infinity, but we know something even stronger. We know that the series of this expression is convergent because even though there are many letters there, it is a geometric series. Something to the power of n, and the something, c minus a above b minus a, is smaller than 1 because of the relation between c and b. But we do have this little fellow here. How do we get rid of it? Now, we cannot say that the series of a and b minus a power of n absolute value is convergent. We only know that it's convergent without the absolute value. But it is enough to know that as a sequence, not as a series, this sequence goes to 0. Now, this series is convergent. And so its general element goes to 0. We know that if a sequence goes to 0, the absolute value of the sequence goes to 0 as well. Mm. And there is I don't know, an epsilon or whatever you like to, n gadol, no, some n, such that for every n greater than n, we have this series is smaller than 1. Then, if it is smaller than 1, when it's multiplied by c minus a about b minus a, we can say that it is smaller than c minus a b minus a. Now for a final great finale. Now, because the series of c minus a above b minus a to the power of n is convergent, it is geometric series with basis between 1 and -1. By comparison test, by the comparison test. We know that the series of an, bn, minus a, blah, 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 is convergent as well. As we already mentioned, this series is actually the series of an c minus a to the power of n. And we actually show that the series is not just convergent. Let's see, it is absolutely convergent. Have that in mind, okay? Let's write it down in a different color. Then I'll let you ask some questions if you like. What do I want you to have in mind? Note. What do we actually prove? We proved that let's call it inside the convergence domain. What do I mean by inside? Not in the ends. I mean, series can be convergent at 1, but not convergent at -1. But inside, for a c smaller than b, that's what it proved, inside the convergence domain, the power series is absolutely, that's right, absolutely, I think, convergent. What we mentioned last week by our friend Weierstrass, it means that the series is uniformly convergent. Now we talk about the uniform convergence of power series in lecture number 17 next week, but I can already spoil and tell you that, as already mentioned before, when it comes to power series, because of the effect here in teal color, all the theorems about integral element by element, integrate element by element, integration element by element, and derivative element by element are true automatically because the uniform convergence of power series is basically always true. We'll say the exact correct things when we get there in the next lecture. Um, any questions about our proof? What come earlier?
Can you just explain the note one more time?
We just explained the what?
The note. Remind
Yeah,
me what saying that the series is uniformly convergent means that
uniformly convergence is what we defined in the previous lectures. The DS,
where
the super,
it converges to a single function.
it converts to a single function, but moreover, the convergence is all around. We draw this epsilon strip or something like that. It is the same all over the segment, meaning that what we defined as the dn, the supremum of the difference between fn and f, goes to zero. And technically, it is what allows us to derivate the series element by element or integrate the series element by element, as we've shown examples last week. But it belongs to lecture number 17. I just wanted to point it out because the main corollary from this proposition. Any other questions?
No, I think it's
Okay. Um, we can move on. How, given some serious AM, blah, 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 how do we find R? Then how do we use R to find what the exact domain of convergence is? So that's finding R. A successful prequel of Finding Nemo. How do we do it? We have two basic formulas. I want to explain one of them, then in a note say that the other one is works just fine. Let for less is always great. Let some an x power be a power series. How do we find R? So in infi number one, which is very fun, we had two basic convergence tests. One of them was the D'Alembert's, don't say it exactly in English, the mana, an plus 1 above an. We calculate the limit of it. It's greater than 1, it's smaller than 1. And the second one was Cauchy. Cauchy's root test using the nth root of the general element of the series. Which one do you prefer? The an plus 1 above an or the nth root?
or that will be.
Yeah, I don't know. It's whatever you like. It's just the same, basically the same. Let we use. How do we find R? How do we reach these keys? You know this South Park episode? You're not familiar with South Park?
I know what South Park is.
No, it's enough.
Very interesting.
There is like an episode. It's an old one. I probably haven't seen at least the 5 last seasons. But Eric Cartman, he goes to uh, be a teacher in some school. All the students are, black or Hispanic, and they don't know how to calculate 1 plus 1, etc., etc. And his catchphrase is, "How do I reach these kids?" And he teaches them how to cheat on tests in order to get high grades. How do I reach these kids? And you have to put the end of it in Hebrew, it's called shliff. When you have a little note with the formula, something like that, you hide it in your sleeve or something. So how do we find R? We can use using the n what the nth root test. We get the following. L is the limit. Now, if we want to speak about it more precisely, we can say, okay, listen, it's actually the upper limit of the square root. Don't know what exactly errors taught you in the last semester, and I talk about it later. Just want to get to the formula of R. Limit of the square root. No, I don't know any of this one. The nth root of an multiplied by x minus a to the power of n. And here we have the nth root of an multiplied by x minus a outside the root with, of course, an absolute value. And let's denote this one with a different letter. What's your favorite letter from the Latin alphabet?
W.
W. Okay. You can use the Greek as well if you want. I have Greek here as well. It is W multiplied by x minus a. And now we know that if L is greater than 1, the series diverges. If L is smaller than 1, the series converges. Let's write it down explicitly, talking about W and x minus a and blah, blah, blah. So, in other words, if W multiplied by x minus 1 is greater than 1, the series diverges. And if W multiplied by x minus a is smaller than 1, then the series converges. And for my final trick, we can say that if x minus a is greater than 1 above W, the series diverges, and if x minus a is smaller than 1 above W, the series converges. But notice something. What is x minus a to in absolute value smaller than 1 above W? It's actually saying, where's the T? It's actually saying that a plus a minus 1 above W and a plus 1 above w are bounding x from both sides. And of course, x minus a in absolute value is larger, greater than 1 above w, meaning that x is greater than a plus 1 above w, or is less than a minus 1 above w. Let's write it down as well. X is smaller than a minus 1 above w, or I write down with the or the logical notation. So be sure. X plus 1 above w. By the very definition of the convergence radius, 1 above w is the radius. You take one step to the left, one step to the right from A, the series converges. You get out from this interval, this segment, the series diverges. And in the ends, specifically, we don't know what happens. So by the definition, by the very definition of the convergence radius, we get that R is 1 above W. Let's write it down explicitly. R is 1 above the limit of the AN itself without the X. So we have a formula, nice, healthy formula, calculating R. I want to say some things about this formula and what we did along the way. And after I say all of that, we can show an example of some specific given series, calculating R, and then calculating its convergence domain, and we can move on, march forward, each to his own business. Any questions about what we did? So, some notes. It works with what do you say it in English? מבחן המנה.
Quotient.
Yeah, but it's quotient sprites. Oh, it's
Ratio.
ratio. Yeah, exactly. Ratio test. With ratio test as well, the Lambert's ratio test as well. We have that R is 1 above the limit of the ratio, the absolute value of an above n. Of course, using arithmetics, one can say that it is the limit. No, that's why it in B. Okay. First of all, A, you can use the square root, you can use the nth root, you can use the ratio test, and both will do fine. We know that in some cases it is easier, technically speaking, to calculate the nth root, the limit of the nth root. Sometimes it is easier to calculate the limit of the ratio. Whatever you get, you should do the better option. Secondly, by arithmetics, this limit can be written, intuitively speaking, as the limit of the opposite ratio. an above an plus 1. Um, if the limit, uh, if you take the ratio of the root, it's the same. If the limit is 0, then it means that R is infinity, and vice versa. I mean, yes, 1 above 0 is infinity, but it's not really formal. I just wanted to know that it actually works. Um, this is what is good, what works. What is not so good about this theorem? D, we know that these limits do not always exist. The limit of the specifically, looking at the series we mentioned 1 hour ago, where is it? Where are you? Is it? Looking at that, every other coefficient is 0. Yeah, a to n. Oh, Shala. A to n is 0. And the ratio is not defined. Moreover, using the square, the nth root is risky as well. I mean, there are two subsequences here, the odd indexes and the even indexes. Using the nth root is not so obvious as well. Or there are two different subsequences here. So, what can we do? Formally speaking, and technically, actually, what تخلصي, I want to show you speaking. Formally, and probably errors studied that way in Infi 1, we can talk the actual ratio and nth root tests, talk about the upper limit of the ratio or the nth root, and not just the limit itself. Formally, we can talk about the upper, and we need not just we can we tell we need we can and need yeah the upper limit and the lim sub. Let's write down lim sub. You know lim sub, Mr. Leaks. Let's see. Yeah, you know lim sub. About the lim sub and lim inf depends on how exactly errors stated in inf 1. Instead of the limit itself. Here it will probably work. Not about the ratio. Ratio is not defined. We'll divide by 0. Not possible. But is not even defined. But looking in the square root, yes, the square root of all the even coefficients is 0, but for the odd ones, I'm talking about the indexes of the coefficients, of course, it's square root of this one, but on the other hand, technically, calculating the limit of square root of some factorial is not that easy. It's not hard. You can use the ratio theorem that connects between the limit of the nth root and the ratio, but one needs to work a little bit in order to calculate the upper limit here, the limit side. Moreover, or furthermore, we can formulate a way to find R in the general case of x minus a to the power of some bn, and not just n, to mention earlier. Basically, R is one above the limit of not the nth root, but the bnth root. I mean, an to the power of 1 above bn. That's what you put in the denominator. When some years ago, I think it was 4 years ago, I thought it's not called infi, it's called hedva. It's basically the same, but more technical and less theoretical. Course in for the engineers dudes. I showed them this formula. We worked with it, but here in computer science, I don't think we need to get to this technical dirty stuff. What we actually do, I know, tachles, I know, I would have write it in English letters. Actually, using the regular formula on this, considering it to be an and not just a shnei n plus 2n plus 1, will do just fine. So you don't, and I say it as the lecturer, as the one who decides what you need to know, what you don't need to know in order to get yourself a good grade in the final exam. Mathematically speaking, it is a problem. We know it from Infi 1. The ratio doesn't always exist. The limit doesn't always exist. And even if you consider upper limit, sometimes it is infinity, or sometimes you cannot technically calculate it because it's very hard, very difficult. Um, don't lose sleep over these cases. Okay, here in Infi 2, don't need to fight with students about subjects that are mainly belong to the previous course. So proceed with caution, but actually you use the regular formula. Here it is probably much easier to use the ratio one, an plus 1 above an, and this is the denominator of r. You'll get the right answer. Not fine, do not have the time nor the will to dig it more. Why do we get the answer if not say if we divide by 0? How do we it will be fine. But on the other hand, it is important to notice that there are problems here, or problems. It doesn't work all the time, or doesn't work fine all the time, at least. Okay, so I want to use our last minutes for an example. Before we do that, any questions about this note?
Yeah.
Yeah.
Um, when you say regular formula, you mean like the five
Yeah.
condition?
This one or this one?
Oh, right. Okay.
Yeah, not starting with the BN or something weirder.
All right. Okay. So then I'm kind of like, what are you trying to say? Is that we don't really need to worry about general case?
Um, in the bottom line, yes.
Okay.
The bottom line is, okay, I think it's, yeah. Don't want to promise it because mathematically, again, there are problems, but I'll do my best to actually, when I ask you questions, final exam, the regular formulas for R should be just fine. And yet again, the problem of, oh, maybe it's only 2n and not n, and it's bn, not n, is the problem I want you to ignore. But calculating the limit, and it will be hard using the nth root and easier to use using the ratio, or the limit doesn't exist and we need to think of something out of the box. I don't think it's gonna happen, but I'm not saying it will not, period.
Okay.
Don't you worry about it. We have enough material in the syllabus to ask you different questions. Um, okay, let's a quick example. Let's find the radius and then the domain of the following series. Minus 1 to the power of n above n ln n. Number you like?
6.
Okay.
Careful that, Thomas.
What?
Okay. Never mind.
So let's calculate R. We can choose nth root or ratio. We know that the nth root of n goes to 1 when n goes to infinity. And if you don't know it, then welcome. Um, and so it is pretty easy to understand, but it's not trivial that the nth root of ln n goes to 1 as well. Why is that? Because ln n, starting at 3 or something, is on one hand greater than 1, and on the other hand, smaller than n. We mentioned last week that actually even ln n plus 1 is smaller than n. So, of course, ln n is smaller than n. We have that square the nth root of 1 is smaller than the nth root of ln n, which is smaller than the nth root of n. And by sandwich gives us that the nth root of ln n goes to 1 as well. So calculating R, which is 1 above the limit of the nth root of coefficient an, is 1 above the limit of the nth root of the absolute value. Hey, where'd you go? Of the absolute value of our coefficient of this expression. So what does the fox say? What does the absolute value doing? He cancels the minus 1 to the power of n, and because we are running out of time, let's do it quickly. It is 1 above the nth root of n multiplied by the nth root of ln n. Yet again, the minus 1 fades away because of the absolute value. And they all goes to 1, as we've already mentioned and proved. So 1 above 1 above 1 multiplied by 1, which is 1. Clapping, applauding. Next room. So it is 1. The radius is 1. The center of the series is 6. Now we know that the series converges for axes between center minus radius and center plus radius, and diverges for x's outside of this segment, and for x larger than 6 plus 1. One can write, of course, 7 and 5. What happens on the ends themselves on 6 plus minus 1? If we want to check the convergence of the series in the ends, 6 plus minus 1, we do it manually. We just put it instead of x and see what series we get. For x is 6 plus 1, we have if x is 6 plus 1, you are left with the series of minus 1n above n ln n. And we ran out of time, so I write it down quickly and shortly. This series converges. The exact theorem is Leibniz, minus 1 to the power of n, some series that is going to 0. And it is convergent by Leibniz, or Dirichlet, which is the general case of Leibniz. And what happens for 6 minus 1? We have 6 minus 1 here, which is minus 1 to the power of n, multiplied by another minus 1 to the power of n, which is just, let's equal, which is just this series of n ln n in the denominator. And this one is convergent, divergent. We're running out of time, so we're running out of time. By the condensation theorem or by the integral theorem, if you want, that we mentioned.
What's the integral theorem?
The series converges if and only if the corresponding integral of 1 above x ln x converges. And this integral is divergent. We don't have the time to show it, but it is. Trust me, bro. And in conclusion, our last sentence here. In conclusion, the convergence domain is from the river to the sea, from 5 to 7, including 7, not including 5, which can happen, as we mentioned, including the left hand, including the right hand. It's all on the grill, as we say in Hebrew. Okay. We are already late. Any questions about the magnificent material we studied today?
Just serious with a lot of caveats.
A lot of what?
Caveats, like a lot of things to think about.
Yeah, man, it's an important point. We expect you Maybe not to the level of Infi 1, but you are expected to know, be familiar with the convergence tests from the last course. Yeah.
Yes, I
Yes.
forget about it.
No, no, no. First you finish with Infi, then you get the Argazim. That's the right order. Sammy, you do you.
I think left.
Bye bye.